Hello students, in this session we'll talk about inferences in regression and correlation. Regression and correlation is the technique through which we establish a mathematical relationship between two or more than two variables. If we are connecting two variables with each other, one we call independent, another we call dependent variable, or one we call predictor, another we call response. Then we call it simple linear regression model. If we are taking or considering more than one independent variables in our regression model, then we call it multiple linear regression model. So as far as population regression model is concerned, population regression model we write down in this way: alpha plus beta times x plus a disturbance term. This E we call the disturbance term because in real life the relationships between two variables are not as simple as we perceive. Let's consider an example of study time versus marks. So your marks in the exam does not only depend upon the study time that you devote to study a particular subject. Besides that, there are so many other things that your marks may depend upon. For instance, in addition to study time, your marks depends upon your IQ level as well. So I have added one more variable to it, and the model is extended to the multiple linear regression model. So if we are only capturing the variation in marks due to the variation in study time, and if we want to keep this regression model simple, so this disturbance term will capture the effect of all other factors or variables that play a significant role in causing variation in the marks. The sample regression model we write down in this way, either in this form or in this form. Over here, both A cap or A hat or B naught are intercepts of the regression model, whereas B hat and B1 hat in the first and second regression model are the gradient or the slope. So I'm going to fit a linear regression model at the first place, taking this as an example. 13.35. An article read by a physician indicated that the maximum heart rate an individual can reach during intensive exercise decreases with age. The physician decided to do his own study. 10 randomly selected people performed exercise tests and recorded their peak heart rates. The results are shown in the following table, where X denotes age in years and Y denotes peak heart rate. As the first part, determine the regression equation for the data. So I'm going to write down two formulas that you can use. First one for B cap or B1 cap. That's for the slope. The formula to compute the slope or gradient of a regression model is this one. We take the covariance factor in the numerator, that is based upon both x and y, their joint product and the sum, and the product of the sum of two individual variables x and y, divided by SXX, or the sum of or the numerator of the variance formula. This is how we can write down. Similarly, A cap or B naught is equal to Y bar minus B1 X bar. This is how we determine the slope, gradient, or in intercept of the regression model. Now what I have done, I have entered the data in the calculator already, and I have determined these two values directly from the calculator. And the intercept A cap or B naught cap is equal to 222.27, whereas B hat or B1 hat is equal to minus 1.14. This negative sign with the slope indicates that there is an inverse relationship between these two variables, age and peak heart rate. One more thing we would like to compute or determine is the coefficient of correlation, that is denoted with R, and the value is 0.928 or 93, it can be rounded off to. Now, this is how we have determined the regression model, and we can write it down as 222.27 minus 1.14 times x. Now, let's suppose if you would like to predict for a given value of x, that is age, the corresponding estimated peak heart rate. So let's take a value 35 that is not there in the data, but it is within the domain, because when we say within the domain, the value lies between the minimum value of x and the maximum value of x, that is 29 and 46. So I have selected 35 as the value, that is the part of the data within the domain that is available in the data, but that's not included. So how do we predict this? Consider x is 35, which is representing age. So simply we can substitute the value of x in its place in the equation, and then we simply work out the answer. And the answer is 182.37. This is the estimated peak heart rate for an individual whose age is 35 years. Now we are going to test two hypotheses. First regarding slope, another regarding coefficient of correlation. Because if we notice one thing, the relationship between x and y depends upon the slope. and slope should have a non-zero value. Whether it is a positive relationship or a negative relationship, it should not be equal to zero. And hypothesis test, we know that we always perform for a corresponding population parameter using the sample information. So testing or for a useful predictor. And the statement that we should be looking in the question for this particular hypothesis testing, let's assume that as part B, I did mention in the question, test the hypothesis at 5% significance level that age is a useful predictor for the peak heart rate. So this statement should be given room in the alternative hypothesis for which the corresponding population parameter should be set not equal zero. And we can copy the statement of hypothesizing here as age is a useful predictor of peak heart rate. H naught we state as beta equals zero, and that would be the negation of the statement we have mentioned or written in the alternative hypothesis, that is age is not a useful predictor of peak heart rate. The level of significance that we are given to test this hypothesis is alpha equals 0.05, and since this is a two-tailed test, therefore we need to divide alpha by 2, and that would be 0.025. Now the test statistic that we use for this particular hypothesis testing is T B minus beta divided by SE divided by root SXX, and this denominator part or component measure the standard error of the fitted regression model in terms of the slope. So this is the variation or the standard error associated with the slope coefficient. Now I'm going to write down the formula for these two components separately, and how do we compute SE and how do we compute SXX. SE can be computed as summation y squared minus a times summation y minus b times summation xy divided by n minus 2. Here you can notice that the n minus 2 factor represents the degree of freedom associated with the simple linear regression model because two parameters are involved in the model. Now the formula for SXX is summation x squared minus 1 upon n times summation x whole squares. This is just the numerator of the variance formula that we call shortcut formula. Now, as we know that the associated degrees of freedom for this particular application are n minus 2. So df is n minus 2. Here in this case, 10 pairs we are given in the data, so it gives us 8 degrees of freedom. And alpha by 2 is 0.025, so when we try to locate this value, you can make it confirm, and the value would be 2.306 for T no point no to 5 with 8 degrees of freedom. Same rejection region of no point no to 5 we define on the left hand part as well, and that would take the same value of T with a negative sign. Consequently, the rejection criterion or rule can be stated as H naught would be rejected if T calculated or computed value of T could either be less than minus 2.306 or greater than 2.306. Now we go for computation. And in computation, we need to first work out the value of SE. And as I entered the data in the calculator, we can take the answers for the sum from the calculator as summation y square is 325723 minus the value of a is we have computed as 222.27 summation y. We again can get this value from the calculator as the sum of y is 1803, and then minus b, which is the slope, has the value minus 1.14 times sum of xy is 65865, and divide this by 10 minus 2, that's 8. We can now work out 325,723 minus 222.27 times 1803, and then minus times minus will make it plus 1.14 times 65865. So that's 56.29 should be divided by 8. That's 7.036. And now we take square root of the answer. So SE as a value 2.65. Now we compute SXX, for which we need to know the sum. Summation of x squared. Summation of x I got first. So summation of x has the value 368 squared. Now we go for summation x squared. That's 13968. 425.6 is the answer of SXX. Now we can substitute the slope, which is minus 1.14, minus beta we have taken in H naught as 0. 2.65 is the value of SE divided by square root of SXX, that's square root of 425.6. So that's 1.14 divided by 2.65, then divided by square root of 425.6 is minus 8.87. The computed value of t is clearly falling in the rejection region because it is extremely negative value, which is less than 2 minus 2.306. T calculated is minus 8.87, that is less than minus 2.306, and this is the case of rejection. So we write down our decision as, since T calculated falls in the rejection region, therefore H naught is rejected. And we can draw a conclusion and state a conclusion as the test results are statistically significant at the 0.05 significance level, and data provide sufficient evidence to conclude that age is a useful predictor of peak heart rate. One more conclusion, or furthermore, it can also be concluded that age is negatively or inversely related with peak heart rate, and negative value of T calculated is the evidence for that. Okay. We can now move to the hypothesis testing of coefficient of correlation. Coefficient of correlation we mention as R, or we denote as R, and its corresponding population parameter is rho. So testing for correlation coefficient, and the statement that identify that we need to go for testing of coefficient of correlation is the statement that tests the hypothesis at the 0.05 significance level that age and peak heart rate are linearly correlated. So this should be the statement that we need to write down in H1. But first of all, this is a sample statistic or notation for the sample coefficient of correlation, and this rho is a corresponding population parameter. So in alternative hypothesis, we set rho as not equal 0. In H naught, as a contradiction of H naught, we state it as rho equals 0. And the statement is age and peak heart rate are linearly correlated. Whereas in H1, we write down the statement contradictory to the one we have written down in H1. Age and peak heart rate are not linearly correlated or related. Level of significance is alpha equals 0.05. Alpha we need to divide by 2 because this is a two-tailed test. Critical region, since we are dealing with the same question, same data, that gives us same 8 degrees of freedom as n minus 2 or 10 minus 2 with same 0.025 significance level. So we can copy the same critical region and with same critical value of 2.306 on the right and minus 2.306 on the left, and we can state the decision criteria same as before. H naught would be rejected if T calculated is either less than minus 2.306 or it is greater than 2.306. Now we write down test statistic, and that has a very simple formula. T equals R minus rho divided by square root of 1 minus R squared divided by n minus 2. We can now go for computation, and for this we need to take the value of R, which is coefficient of correlation, from the calculator, minus 0.929, rounded off to 3 decimal places. So that's minus 0.929, take away 0, the value of rho, what we have stated in H naught, and then 1 minus, that's minus R squared, 0.929 squared, divided by n minus 2, which is 8. So denominator, complete answer is 0.131, rounded off to 3 decimal place. So minus 0.929 divided by 0.131 gives us minus 7.09. Again, T calculated is minus 7.09, that is less than minus 2.306. This is again the case of rejection of null hypothesis in the left tail. So we can write down our decision as, since T calculated falls in the rejection region, therefore H naught is rejected. And conclusion we write down as, the test results are statistically significant at the 0.05 significance level, and data provide sufficient evidence to conclude that age and peak heart rate are linearly correlated. Since rejection occurs in the left tail part, it can be further concluded that age and peak heart rate are negatively linearly correlated. That's all from this lecture video.